Okay, so as you can see in the title, I'm going to talk about Chern-Simons theory and spin foam with cosmological constant. And I want to first give you some references for these lectures. And basically, I want to use some techniques in Chern-Simons theory to build up a spin foam with a non-zero lambda. And mainly, the references I use for these lectures are the first and to fourth. And 5 and 6 are some more recent developments, but I don't think I will have time to go to that part. So I'll base on 1 to 4 references. So the records should be given to the authors of these references. As you can see from the titles of these references, you will see SL2C Chern-Simons theory, and the technique related to SL2C Chern-Simons theory. The references for these techniques can refer to the 7 to 9 references. And I also created a lecture note for this lecture, which have more details because I can't go through everything. And I think the lecture note is already uploaded to the website, so you can check that out. And the references are also in the lecture note. Yeah. So in these, I have 3 hours of lectures, 3 lectures. And my plan for the lectures are the following. And in the first lecture, I've decided to just write it during my lecture. And in the first lecture, I would talk about the motivation of building up the spin foam in this way. And I will talk about the scheme of how we build up this spin foam model. And in the second lecture, I would talk about the SL2C Chern-Simons theory on a so-called ideal tetrahedron. I will explain what is an ideal tetrahedron when we get there. And in the third lecture, I will generalize it to talk about SL2C Chern-Simons theory on a 3-manifold, and I will tell you what this 3-manifold would be. And then on this 3-manifold, we will build up the spin foam model. We will write out the spin foam amplitude in 4 dimensions. We'll talk about the 4D quantum gravity. Okay, let's get started. And in this first lecture, we talk about the motivation. Okay, so maybe just very briefly, what is the idea of spin foam? So the spin foam is to provide a way to regularize the path integral of gravity. So formally, we'll write a path integral of gravity with the integration for the metric, that's a degrees freedom, and exponential of I, Planck over Planck length squared, and the Einstein-Hilbert action, which is a function of the metric. So it is described, if I have describes the history of manifold. Suppose I have a initial slice and I have a final slice, then this path integral describes the history that is bounded in this spatial slice. So this describes a 4-manifold M4. And of course, I will put some boundary condition, which is the induced metric on the initial slice and the induced metric on the final slice. So this is the formal path integral, but now we want to regularize it. And after regularization, we arrive at the spin foam amplitude, which depends on the triangulation of this 4-manifold, such that it respects the so-called local spin foam ansatz. What is local spin foam ansatz? It assumes that this amplitude, which is defined on a triangulation of a general 4-manifold, it can be split into some local amplitude. In particular, after the triangulation, we will have some simplices. So for each simplices, I will associate an amplitude for the simplices, and it has a function of some configuration. Now I will just refer to the EPRL model, and the configuration will be spin and some intertwiner. And I associate an amplitude for all of them, so I will have a product to all the 4 simplices. And furthermore, we will associate the amplitude for each tetrahedron of the triangulation. It's also a function of spin and intertwiner. Also product for all tetrahedra. And also for each triangle in this triangulation, I also associate the amplitude to the triangle, and this in EPRL is just a configuration. It's a function of the spin, and also product for all of them. And then I sum over all the configuration. This is a local spin-form ansatz, and in 4D spin-form, we are more familiar with the spin-form model with with zero cosmological constant. And here I will just refer to the EPRL. This is one of the most studied spin-form model in 4D. And one feature of the EPRL spin-form is that when the configurations J, which we call spin, goes to very large, we find that the amplitude for simplex, it's reproduced the redshift action, which Bianca taught you in her lecture. And she told you that the redshift action can be seen as a discretized Einstein-Hilbert action. And it's this result that tells us the EPRL is some kind of quantum gravity theory. But the problem in the EPRL is that if I consider the spin-form amplitude in EPRL for a general triangulation of a four-manifold, it gives us a divergent result. So how to deal with it? It's not a very good regularization in this way. So usually what people do is to introduce a cutoff. Because this divergence comes from an infinite sum for the spin, it sums from 0 to infinity. So we introduce a cutoff. Instead of to infinity, we sum from 0 to a maximum J max. Then this gives us a final result. But this cutoff is put by hand. So one may ask, what is the physical meaning of this cutoff? And today we will talk about the 4D spin-form model with a non-zero cosmological constant. And that thus gives us a finite amplitude. And this also gives us a physical meaning of the cutoff, because now I tell you a cutoff because at the end the expression also has sum over configuration from 0 to some finite number. And we already, before this spin-form model, we already know an example in 3D with a non-zero lambda. In an example in 3D, the spin-form, we have the Qiaoyin model. And this corresponds to a positive lambda, and that also gives us a finite amplitude. So we also have a very nice result in lower dimension. But the center of this lecture is to tell you the four-dimensional spin-form with a non-zero lambda. And actually, to build up this spin-form, we learned some idea from the EPRL. So I think it's also good to give you some review on EPRL, although you've heard this in previous lectures, but I will explain it in a way that's more parallel to how I would generalize it. So EPRL, again, it's with a 0 lambda. We work on the Lorentzian signature. So the signature would be the -1, 1, 1, and 1. And if we consider the first order action for GR, it's a function of the tetrad and a connection. This E is a tetrad, and this is an SL2C1 form. And this A is a connection. It's also an SL2C1 form. And this action is written as an integral for the four manifold. And I have 1/2 here, and epsilon ijkl, ei wedge ej wedge curvature, which is a function of connection. And here ijkl, they are Lie algebra indices. And I have 1/2 in front because I've taken the 8 pi g equals to 1. And we know that this equation of motion of this action is not changed. If I just add a host term, then it gives us a host action, which is also a function of E and A. Then I just add, so starting from this action, I add what minus 1 over gamma and epsilon ijkl, and I have the Hodge dual acting on E wedge at, E wedge E, and wedge F. Okay. And this gamma is called the Barbero immersive parameter. And we take it to be a real parameter. And this Hodge dual, if I act on two forms, say x, then it acts in this way. So 1/2 epsilon ijkl xkl. Because we are in Lorentzian signature, so Hodge squared equals to -1. And this host action can be written as a the action of a topological theory with a constraint. And this, so I'll call it equation 1. And 1 is, this topological theory, the action is a BF action. I'll call it HBF, because host, BA. And this B is an SL2C 2 form. And it's written as, now I want to get rid of the indices, so I would just write it into a trace, M4, and a trace of Hodge plus 1 over gamma, act on B wedge F of A. And with a simplicity constraint. And this is B equals to plus or minus E wedge E. And here the trace for if I have two forms x and y, this is defined as xij times yij. So in spin form, we would like to, because it's topological theory, it's much easier to do the quantization. So in spin form, we would like to first quantize this topological theory and then impose the simplicity constraint quantumly. So we want to first do the quantization, this host BF theory, and then impose the simplicity constraint quantumly. So what does it mean by impose simplicity constraint quantumly? We know that from here, the simplicity constraint is B equals to plus or minus E wedge E. So E wedge E is a triad, it's a function of the matrix, so it encodes the geometry. So imposing simplicity constraint, it's just to generate some geometry. And quantumly, it means that we want to generate quantum geometry from a topological theory. So let's do the quantization. The quantization we do is the path integral quantization. So we construct a path integral for this BF theory. So then I have e to I over LP squared and this action. And if we first perform the integration for B field, then we notice that it becomes an path integral, an integral over A field of a delta of the curvature. And of course, it's just a formal expression, just to give the idea. If we can now consider a 4 manifold with a boundary, so partial M4, then I need to impose a boundary condition. And imposing boundary condition is the same as coupling with the boundary state. So now I'm left with a dA. So I would like my state to be a function of the connection and on the boundary. So here the A partial, it is the connection located at the boundary. When we have the boundary state or boundary condition, then this partition function, this path integral can be seen as a state. I will call it BF state. Then the BF amplitude is defined as the inner product of this boundary state and this BF state, and or explicitly just integral of delta of curvature and then couple with the boundary state. And what boundary state should we choose? We know that an LQG provides a good way to regularize gravity, so we get some insight from LQG, canonical LQG. So we want to choose this state to be such that has a support on a graph. And also, I want to choose such a state through, it's a function of a connection. I want this state to be a function of connection through some holonomy along some loops. And this is what we call the SL2C spin network state. And here the gamma, the graph, is on the boundary of the four manifold. Now I want to, as I told you, I want the spin form amplitude to respect the local spin form ansatz. So first, I want to construct the amplitude for a four simplex. So now we just consider this four manifold to be a four ball whose boundary is a three sphere. And the triangulation of a four ball gives you a four simplex. I denote it by sigma. And the triangulation of a three sphere is a collection of 5 tetrahedra that are glued together, pairwise. And on this four manifold, I can construct the amplitude for four simplex. And here, the gamma in this case becomes a so-called gamma 5 graph. And this gamma 5 graph is the 3D dual of the triangulation of a three sphere. Let me just project, in what sense are they 3D dual? Let me just project this triangulation on the two plane. It has 5 vertices. Let me try to draw it nicely. Yes. And I have 1, 2, 3, 4, 5, and 10 edges. Now I already have 5 edges, and then 6, 7, 8, 9, and 10. And let me also, then this gamma 5, let me also project it on the plane, and it has 5 nodes. Let me first draw 3, and another 2, I'll put it inside the triangle. Because nodes are not the same as vertices, so I denote them differently. I will put a bar, 1 bar, 2 bar, 5 bar, 3 bar, 4 bar. And in what sense are these two are 3D dual? It's in the following sense. So I draw a table of them. The left column is a triangulation of 3 sphere. And the right, I have the gamma 5 graph. And they are dual in the sense that for each tetrahedron in the triangulation is dual to a node in the gamma 5 graph. For example, a tetrahedron has 4 vertices. For example, the tetrahedron formed by the vertices 1, 2, 3, 4. It's this tetrahedron, and it's dual to, for example, node 5. And each triangle on the left column is dual to a link of the gamma 5 graph. For example, I have triangle bounded by vertices 1 to 5, and it's, for example, dual to the link bounded by 3 bar, 4 bar. And go on, and the edge on each edge in the triangulation is dual to a face. For example, I have an edge connecting 4, 5 is dual to the face bounded by 1 bar, 2 bar, 3 bar. And we don't go on because graph is too complex, and so at most it has a face. Okay, in this example, let's write the BF amplitude for four simplex. And this is, again, just a special example. So I have the state on the boundary, which is have support on the gamma 5 graph, and inner product with the BF state. And on this amplitude, we want to impose simplicity constraint. And we impose it on the boundary. In particular, we impose it on the state, the gamma 5 graph state. How do we impose it? It must be imposed in a way that it can be realized as some regularization of the continuous simplicity constraint. So it must be a regularized B equals to plus or minus E wedge E, right? And here comes one key idea in this spin form, and it's that in a bulk of this for simplex, it is topological, it's just a BF theory. And geometry only appears on the boundary of the four simplex. And this is in the same idea as the Reggie calculus that Bianca told you, because all the degrees of freedom calculus, they are on the boundary. Okay, now, the simplicity constraint is B equals to plus or minus E wedge E. It's a two forms constraint. So how do we impose it? After triangulation, it's natural to do a smearing over a face because two form. So we integrate this B field over a triangle which is in a tetrahedron. And we define it to be a triangulated B field. Then we can discretize this simplicity constraint. The discretized simplicity constraint gives a relation between the discretized B field and the tetrad. And this EI, EJ of T, they are in a Cartesian coordinate patch that covers the tetrahedron. That covers the tetrahedron. And this is not yet the simplicity constraint we really use in the E power L, but instead we want to write them in an equivalent condition for the discretized B field. There are two conditions for the discretized B field that is equivalent to this. The first one is that, so there should exist a vector in R13 such that, and all the discretized B field in a tetrahedron is orthonormal to this vector. So it equals to 0 for all F in a tetrahedron. And second, if I sum over for all the triangle in a tetrahedron, then this discretized B field gives us 0. And this is called the closure condition. And because you see that this constraint is associated to a triangle and encodes some geometry. So this B equals D wedge E just encodes the geometry of a triangle. And so encodes the geometry of a triangle in the sense that it tells you the normal and the area of a triangle. And this, we defined the area of a triangle times the normal of the triangle, normal vector, and it's equals to 1/2 epsilon ijkl. And this 4 vector times the discretized B field. Then if I write it in this way, then the closure condition can also be written as the sum over for all the triangle, the area times the normal vector equals to 0. And from here, you've heard the Minkowski theorem from Francesca's theory. According to the Minkowski theorem, we know that this identifies us a convex tetrahedron. And these two requirements, these two conditions for a discretized B field are really the simplicity constraint we impose on the E-power spin form model. There's a question?
So for what I've been learning these days, at least with Francesca's talk, she was like pointing out about this constraint that in the projective limit could be like the Gauss constraint. So I'm always confused because I see like in this type of models or theories that there are always constraints, but I don't know if actually they are all coming from like a first class constraint. like if you get like a limit, could you get a first class constraint? Or we could say that they're like different terminology, that one thing is like the first class constraints that are related to gauge transformations, and these are like just geometrical constraints, or are they actually somehow related?
In EPRL, there are two kinds of constraints. Some are first class, some are second class. And in quantum level, we will impose them differently. They are not all first class. And related to Gauss constraint, the Gauss constraint will generate the rotation, and it's more like the closure condition. Because the closure condition is the identify a tetrahedron and also up to a rotation.
But then all these geometrical constraints that you're getting are coming from either the first or second class constraints.
It comes from, it's just a reinterpretation of this constraint, the B equals to E/E. And B equals to E/E comes from discretized B, the simplistic constraint from the continuous limit, continuous theory.
Thanks.
Yeah. Okay, maybe I can give you well, it's very easy to see why the simplistic constraint has to be written into 1 and 2. Because I told you, what is simplistic constraint? It tells you the geometry. Now we have discrete, we have triangulation. Then simplicity constraint is to generate some discrete geometry from a topological theory. Or basically, we want to encode the geometry of a four-simplex from a topological theory. And what is four-simplex? Now B equals to B/E. B just say some geometry of a triangle, F. And if I give you 10 triangle, how do I form a four-simplex? So first I need to form a tetrahedron. And a tetrahedron is a 3D object. And I have give you a 4 triangle in a 4D space. And then if I want them to form a tetrahedron, they must live in a 3D subspace. That's why we have the first condition. In a 3D space, we must be able to find a common normal to all these 4 triangles. And that's not enough. We want them to form a tetrahedron, so they must be close together to form a close boundary of something. That's why we have the closure condition. And this is the intuition, and this is the geometrical interpretation of these 3 conditions as a simplicity constraint. Okay? And now we have the discrete version of the simplicity constraint. Then we just do the quantization. But I don't need to go on because this continuous discuss and the discrete discuss is enough for us to generalize. So I stop here, and you already heard the quantization part from previous lectures. Okay, we want to do the same thing, but at the non-zero lambda. Okay, the first thing to do is to construct the path integral. So we discussed the path integral of 4D gravity with a non-zero lambda. And in this part, we just want to have some formal discussion, okay? And starting point is also a first order action. Now I have a lambda, so I call it H lambda BF. It's also a function of the B field and the connection. And again, this B is an SL2C2 form. And this A, its connection, is an SL2C1 form. And it's written as an integral for the 4 manifold and trace of Hodge plus 1 over gamma, and B wedge f of A. This is the action we had before. But now I want to add a cosmos constant. So we have a volume form. And this is the action. And if I impose the simplicity constraint, now it's B equals to sine of the lambda times E wedge E. I write the lambda and wedge in the same way, but you should be able to distinguish them very easily. And if I just write it, then this action will become a host action, which is a function of tetrahedron and connection. So this is correct action. And you notice that I've put an absolute value in this action. And in some literature, some literature don't put this absolute value. But we put it here on purpose. Then the simplicity constraint has a sign here. Why do we put it on purpose? Because the BF theory is a topological theory. And as in EPRL, we would do the quantization, discretization, and a lot of stuff. And imposing the simplicity constraint is the last step to construct the spin-form model. So if I put an absolute value here, then whatever we do, as long as we haven't imposed the simplicity constraint yet, it's suitable for either sign of the lambda. So we actually get benefit of it. And we'll see this benefit in the third lecture tomorrow. And okay, this is a BF action. Let's consider the equation motion by doing the, with respect to the B field. And the equation motion, we find that it gives a linear relation between the curvature and the B field. And if I impose a simplicity constraint here, I get a relation between the curvature and the tetrad. And let's look at this formula. On the left-hand side, this is the, in the field language, is the field strength. But on the right-hand side, it's the E wedge E. So we have geometry. And this is the key. This gives us some key idea how to impose a simplicity constraint later. So let's keep this in mind for now and go on. Now I have the action. I want to do a quantization using a path integral. So I consider the path integral, dAdB, for an exponential of I over Planck's length squared. Then I can copy the action here. And this is the path integral. Then you notice that, oh, we have in the exponent, we have B wedge E. This is the form of Gaussian integral. Although it's a formal, so we are not really doing a Gaussian integral explicitly, but we know that performing a Gaussian integral is the same as imposing the equation motion. And we know equation motion is F equals to epsilon lambda over 3 times B, or I can inverse it, B equals to 3 over epsilon lambda times F. We just plug in. Then this becomes a path integral of this action. The coefficient is, if you calculate carefully, 3I over 2 epsilon lambda LP squared. And then in the integral, I will have trace of host plus 1 of gamma, and then F wedge F. Now you notice that it's a F wedge F is in the form of a second Chern term, which is topological. Then it should be we should be able to write it as a path integral of Chern-Simons theory. It looks like that, but we still have this Hodge action, so it's not quite. But we still want to relate to Chern-Simons theory, as you expect from the title of this lecture. How to do that? We just do the decomposition of this F field. So we decompose this F, I wrote curly F, into a self-dual straight F and the anti-self-dual part. This straight F, the self-dual part, is defined as 1/2, 1 minus Hodge dual, I Hodge dual, acting on the curly F. And the F bar is defined similarly, but with a plus. And why is it self-dual? Because Hodge dual acts on the F equals to IF, and the Hodge dual act on F bar equals to minus F bar. And or you can also decompose the connection to the self-dual anti-self-dual part. Then you realize that the straight F is a function of the self-dual connection, and the F bar is a function of A bar only. Then, if you do that, you notice that this path integral can be written as the dA bar, and we have the exponential of minus 3 over 2 L Planck length squared epsilon lambda. Now we see we can decompose it into two terms. One term is 1 minus I gamma, because this separation allows us to remove the Hodge dual, and we have trace of F wedge F. And another term, which is in terms of only F bar wedge F bar. Great. Now we have the second Chern term. If we consider this four manifold with a trivial topology, then this path integral can be written as a path integral of the Chern-Simons theory on the boundary. So it becomes a dA on the connection on the boundary, because we integrate out the bulk term, and exponential of Chern-Simons action. We have two terms. One is action of A, another is the action of A bar. And they are defined as follows. As Chern-Simons action for A is defined as a coupling constant over A pi, and then I have an integral of the boundary of the four manifold, and then trace for A wedge dA plus 2 over 3 A wedge A. This is the Chern-Simons action. And this is for the Chern-Simons action for the self-dual part of the connection. And for the anti-self-dual part, I just put a bar on top of them. So I have bar, T bar, A bar, A bar. And what is T? T is a coupling constant. And it's a complex coupling constant, actually. So it has a real part. It also has the imaginary part. I would say S. And T bar is a complex conjugate of it. And if you figure out the coefficient carefully, then you find that K equals to 12 pi over Planck length squared, gamma, which is the Barberi-Merzi parameter, and absolute lambda. And the S equals to gamma times K. And actually, there's some restriction for the real part of this coupling constant. And because if we require the partition function to be gauge invariant, okay, then to figure out that, let's consider the gauge transformation. So we consider gauge transformation for the Chern-Simons action. So we have the connection goes to G inverse AG plus G inverse DG, and where G is in SL2C. And if you do that, plug in the action, you will find such a term in this way, which is a function of the gauge group element. You have 1 over 24 pi squared, and then trace for G inverse DG, wedge G inverse DG, wedge G inverse DG. You'll find this term. And this is called the winding number density of the element G. And if I integrate out this over a 3 manifold, and this gives us a integer. And this integer is called the winding number. And this we get this for a 3 manifold. For a 3 manifold, which is a closed manifold with no boundary. So this just tells you that Chern-Simons theory is not gauge invariant under a large gauge transformation. Instead, under a large gauge transformation, we have the Chern-Simons action would add a term, which is 2 pi case n. This K is the real part of the coupling constant. But we can lower our requirement, although it's not gauge invariant under large gauge transformation. We can just require the path integral itself is gauge invariant. So we require e to the I as the Chern-Simons action. We just want this to be gauge invariant. And this requirement would demand that the real part of the coupling constant to be an integer. So this discussion, just to tell you that the K here has to be an integer. And then this imaginary part is a real number. And this is discussed in Witten's paper in 1991. And it says that when the coupling constant of the complex Chern-Simons theory, the real part is an integer and the imaginary part is a real, then we will get a unitary Chern-Simons theory, unitary quantum Chern-Simons theory. Okay, so after that, let's continue. Where are we? Well, we were here. So this is the path integral of Chern-Simons. We end up with the path integral of a Chern-Simons theory, and it's a boundary condition, so we'll call it the Chern-Simons state. Let's go back to spin form discussion. And then I will have, then to define a spin, an amplitude, and then I just couple this state with a boundary state. Now it's a boundary state of a connection A and A bar. And then, or explicitly, it's a DA bar. I just plug in let me also denote this action. It has a complex Chern-Simons coupling constant. So I denote it by T, which is a function of A and A bar. Then I consider the e to minus I as T.
Qiaoyin, we have a question.
Yes, let me finish this line and couple with a state, A bar. Yes?
Yes, thank you. If you go a little bit up, when you have the decomposition, a little bit more up, there, where you have 1 minus I over gamma, and then Chern-Simons of self-dual and anti-self-dual.
Mm-hmm.
So you could also write this instead of Chern-Simons as a Gauss-Bonnet term, right? So you will get an extra factor of I on each one of them. So my question is, how, like, first, if this was a choice because of the techniques that follow?
Yes.
I see.
That's true.
So what will happen if you did the opposite and leave it in terms of a Gauss-Bonnet term?
That's basically because we want to use some Chern-Simons technique. So this is just a formal discussion. It's not very concrete. We're just a formal path integral. But if I do another way, it will lead us to another way to construct spin form, which I'm not aware.
So it will lead to different conclusions, for example, on this K?
Maybe. I'm not sure.
Okay, thank you.
Yeah, but I think that's another direction.
Okay.
Okay.
Thank you.
Okay, let's continue. So here I have the state, which is a function of AA bar. And on this state, as in EPRL, I want to impose the simplicity constraint, which are at the quantum level, because we have a partition function. So we want to impose the quantum simplicity constraint. Simplicity constraint. And now we are led to a Chern-Simons theory. Let's do a little bit of the canonical analysis. So of Chern-Simons theory, if you are not familiar with it. So the canonical analysis. We consider locally for the local patch of this boundary. Then I can decompose it into a 2D space times R. Then I can write this complex Chern-Simons theory with a complex coupling constant into this way. So it becomes an A0, I single out the zero component, and also the anti-self-dual part. And here I equals to 1 and 2, because we are in 3D. Then we can write out the symplectic form of this Chern-Simons action, and it gives us T over 4 pi integral for the 2D space. We have the trace of delta A, straight A, right, delta straight A, and plus the other part, the complex conjugate part, or the anti-self-dual part. We have this. And with the symplectic form, we can derive the Poisson bracket. Then eventually, I get the Poisson bracket for the A field in this way. Equals to 4 pi over T, epsilon ij, and the 2 dimensional delta. And this is for A, and we have the same thing, similar thing, for the A bar, but just put a bar over it. And the T bar. And the A and bar, they commute. They Poisson commute. Okay? And this x and y, they live in the 2D space. Then we can also consider the Chern-Simons equation motion. So I would do the derivative for the A0 component and also for the anti-stability part. And it gives us the 0 curvature. So this tells us that the equation motion of Chern-Simons gives us the 0 curvature. But I told you before that the simplicity constraint, on the other hand, tells us that f, instead of 0, gives us a lambda over 3 E wedge E. And now we're in 3D. So the left-hand side gives us a magnetic flux, or generalization of magnetic flux. And the right-hand side, again, it tells us geometry. So they conflict. So what does it tell us? Then we need to, this means that somewhere in the manifold, we need to introduce some defects. And now we have the Chern-Simons theory on the boundary of 4 manifold, and these defects are introduced on the boundary of the 4 manifold. So here comes the punchline of this discussion. The punchline here is that now at the beginning we want to construct the particle of 4D gravity with a non-zero lambda. So the 4D, it should give us a 4D quantum gravity with a non-zero lambda, which is on a 4 manifold. And this can be represented by a quantum Chern-Simons theory with a complex coupling constant. Here's the T and T bar, which is on the boundary of this 4 manifold with some defect, which is on the boundary of this 4 manifold. And this is a key point after this discussion. We want to use this idea to build up string form. Firstly, we want to build up the amplitude force for a 4 simplex. So now we consider the 4 manifold to be a 4-ball, and whose boundary is again is a 3-sphere. So I can simplify this punchline. So 4D quantum gravity with a non-zero lambda on a 4-ball can be represented by quantum Chern-Simons theory on a 3-sphere and with defect on a 3-sphere. Then let's go on. As in EPRL or other spin form model, we do the triangulation. The triangulation of a 4-ball gives us a 4 simplex, and the triangulation of this boundary gives us the 5 tetrahedra. And now we also, after the triangulation, we also want to triangulate the discretized simplicity constraint, which is f equals to lambda over 3 E wedge E here. And it's also a 2-form constraint, so we will also want to integrate over a triangle. So I will get, then this defined as a discretized curvature or associated to a triangle. And then we, as in the EPRL case, we can also write the regularized simplicity constraint to be the discretized curvature equals to lambda over 3 and EI of t, which EJ of t. And again, this is the tetrad on the local patch of the covering a tetrahedron. And we want to now, as I said, we want, before we do discretization, this simplicity constraint should introduce some defects. Now we also want to introduce defect after the discretization. So we want to interpret this as some defects on the triangulation of the 3-sphere now. Then you think, what kind of defects should we impose? Because it's associated, it's a 2-form constraint, so a natural thing is to introduce maybe a phase defect. But the problem is that we are not very familiar with how to impose, how to deal with phase defects. We are more familiar with the lower dimensional defects, for example, a link defect, a node defect. How do we do that? We remember that we have the duality map. A triangle is dual to a link, and we know how to deal with a one-dimensional defect. So how about we just put this dual graph to a three-sphere? So let me copy this graph here, and I want to embed this gamma 5 graph to a three-sphere. I would denote this to be a three-sphere, and this is gamma 5 graph. So I embed my gamma 5 graph to a three-sphere, and then I will impose the simplicity constraint on the links of the gamma 5 graph. Then after I do that, I can always take the dual picture and interpret it as the defect imposing on the triangle. Okay? So now we know how to have an idea how to impose it, the simplicity constraint in a discrete level. Then the next thing is to do the quantization. So we want to quantize this constraint to be an operator, something like this, and then we insert it to the partition function we got before, which is associated to a for simplex. And now comes the second idea to build up the spin form, which is that instead of an operator, we insert it along a defect, which is along a graph here. But this can be replaced by another thing, which is first, we remove the graph. And the graph and the tubular neighborhood, tubular open neighborhood of the graph. And then we impose a boundary condition on the graph complement. And the graph complement just means that I just remove the graph from the three manifold. And this comes as a second idea to build up the spin form model. And here in our example, my three manifold is three sphere, and I remove the graph complement. I would denote it by three sphere quotient of the open neighborhood of the gamma 5 graph. I would just denote it by S3 quotient gamma 5 for simplicity. And what kind of boundary does it have? So the boundary of this three manifold, graph complement three manifold, has two parts. So the first part is a four-hole sphere. I would denote by sigma 0, 4, 0 because the gen is 0. And this is created by removing the nodes. For example, I can remove one node, and because there are three links that connected to this node, so it becomes a four-hole sphere. And I have four nodes. I remove four nodes, then the number of this, the number of four-hole sphere is 5 on the boundary of this three manifold. And another kind is the annuli. And this is created by removing a link of the graph. For example, this link, I remove it, then the boundary becomes an annulus. I have 10 links, so I have 10 annuli on the boundary. Okay, so now I want to combine this idea and this idea together. And what does it tell us? It tells us that a 4D quantum gravity with a non-zero lambda on the 4-ball, it can be represented by a Chern-Simons theory on the gamma 5 graph complement of three sphere with a boundary condition. Of course, we want the boundary condition to encode the simplicity constraint. So with the simplicity constraint somehow imposed on the boundary of this three manifold. And this is the key eventual, the final idea, the combined idea to build up a spin form model with a non-zero lambda. Now it's clear that to build up the spin form model, build up the spin form amplitude as in the E power L, we have two tasks. task 1 is to construct the Chern-Simons partition function on this 3-manifold, which is the gamma 5 complement of a 3-sphere. And I will talk about this in my second lecture. And the second step, the second task, is to impose a simplicity constraint on the boundary of this 3-manifold. And I will talk about this in, we will get there only in the third lecture tomorrow. And any questions so far? Yes.
Thank you. My question is, you said you had to impose defects, and for that you introduced not the boundary, but the dual to that, and you wanted to introduce defects on the vertices or the nodes, perhaps. Can you re-explain how do you do that?
Why do we do it, or how do we do that? I haven't explained how we do that yet.
Oh, okay.
Yeah.
Yeah, I understand the why, but the how was the problem.
Why we do that?
No, the why was clear, but the how was the problem.
Okay,
but I guess you didn't. Yeah,
wait
okay.
for tomorrow.
Okay, thanks.
Any other question? Yeah.
Yeah. My question is about the boundary of that manifold S3 complement the gamma 5 graph. You said that we get, one of the cases is that we get 4-hole spheres, 5 4-hole spheres. Can you explain how that happens again?
Because, well, you have to imagine it's three sphere. It's 3D, it's easier to imagine than 4D. So I just remove one node and I take out open 3-ball, then its boundary is a 2-sphere. But because this node is connected to 4 links, so I will have, oops. Okay, be careful. And then I will have one hole that's connected to one link, 2, 3, 4, 4-hole sphere. Yeah.
Right. Right. So, is this what we get? Is it like of different 4-hole spheres, or like is it a union of 4-hole spheres? Like in some way glued
the
together?
boundary is a union of 4-hole sphere and the union of 5-hole sphere and 10 annuli.
Right.
That's
And
the full boundary.
right, and it's not a disjoint union. I mean, those 4-hole spheres, they may be
distinct.
glued to
They
each
are not
other.
connected. They are not directly connected. They are connected by the annuli.
Right. Okay. Oh, thank you.
Is my time up?
It is, yes.
Okay, I think it's a good time to stop.
So,